for coming, and thank you to the organizers for the invitation. So my goal here is to introduce shifted tableaux for those who haven't seen them, to present them in their various flavors, and sort of situate them in a geometric context that is perhaps heavily biased towards the things that I know as opposed to the places that they show up. So with that said, let me begin. And I want to begin just by reminding everybody about Tableau, which we've been seeing over the course of the past week. Those of us who've been here and those of us who haven't, I hope have seen them before in other circumstances. So I want to think about semi-standard Tableau, and we have one in purple on the left. A semi-standard Tableau, right, the labelings are weakly increasing across rows, strictly increasing down columns, at least in my preferred conventions. You associate a monomial, which comes from the entries of the tableau, right? So we have two ones, that's why we have an x1 squared. We have a 4, that's why we have an x4, and so on. And then if you sum them all up over some shape lambda, you get a Schur function. So this, and I think we've sort of learned that Schur functions are very lovely and important in the context of Schubert calculus, right? They represent cohomology classes of the Grassmannian. We'll talk more about geometric aspects of this later in the talk. Okay, so I also want to mention RSK just as a bijection of Tableau. The idea is that you take a byword. The details are maybe less important. I'm not going to insert anything this entire talk. But just what's important to recognize is you're talking about taking some sort of word-like object and mapping it to a pair of tableaux. And that's going to happen a whole bunch, by which I mean in the abstract as maps, not in the examples. And then what's lovely about RSK, amongst many things, is that the two tableaux that show up are essentially the same type of object, right? The P object knows a Schur function. The Q object sort of knows a Schur function in some sense. Okay. So where I'm going to go next is I want to talk about Stanley symmetric functions. So these showed up at the very end of Dave's lectures, for those of us who were there, as a specialization of these backstable Schubert polynomials. In the interest of brevity, I'm only focusing on the Stanleys, but pretty much everything I'm saying can also be extended to that generality. So I have this definition. It's pretty complicated, but what it boils down to is for every reduced word in your permutation, you get a fundamental quasi-symmetric function like Vasu was talking about this morning, and you add those all together, and that's a symmetric function. So these were introduced by Stanley in, I believe, 1984, and they were completely divorced from geometry. His motivation was to count reduced words. And you can check from this definition that the coefficient of like x1, x2, dot, 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 xn, that's going to be the number of reduced words for your permutation. And then Edelman and Green proved that these Stanley symmetric functions are Schur positive. His proof is via a variant of RSK called their proof, I should say, is a variant of RSK called Edelman-Green insertion. And here it's like RSK, but your P object and your Q object are actually different. Your P object is what's called an increasing tableau. It's strict in both directions. Your Q object is a semi-standard tableau, so not strict in the rows. And then this A lambda W coefficient, this is the counts sort of possible P for a given tableau. And we'll do an example of that momentarily. I do want to comment on this LS85. So when I first talked about Stanley symmetric functions in front of a large audience about a decade ago, Alain Lascaux yelled at me. He said, "You're citing me incorrectly. You should attribute this to me." And he's kind of right. There's another approach to computing these Stanley symmetric functions based on the transition equations that Anna introduced at the start of all this and have, I think, been used since. The issue is connecting Schubert polynomials to Stanleys. It's not very difficult. All you would do in that fundamental quasi-symmetric function area is you would insist also that ik should be less than or equal to ak. If you add that extra condition, the Stanley symmetric function is a Schubert polynomial for W. And so if you can write Schuberts in terms of other Schuberts, you can write Stanleys in terms of other Stanleys and sort of inductively prove this symmetry. And we'll do an example now. OK, so the main point I want to emphasize here is that Stanley symmetric functions know the Littlewood-Richardson rule. And in fact, they know quite a few families of Schubert structure coefficients. There's a recent paper by Daoji Huang where she proves the separated descent case that Alan was talking about, essentially using Stanley symmetric functions. It's a little more complicated than that, but only a bit. And so here's an example. So our Stanley symmetric function for 3, 2, 1, well, we have this tableau, 1, 2, 2. And if you read it from bottom to top, left to right, right, so first row, the second row is 2, the first row is 1, 2. That's a reduced word for W. And so in general, we want increasing tableau whose reading words are reduced words for W. That's what these coefficients are in this A lambda. And so F321, the Stanley symmetric function, is just the Schur function of shape 2, 1 because this is the only such tableau whose reading word is a reduced word for this permutation. Likewise, F312, we get S11, and it's possible that my conventions are inverse from the typical ones. So if that's the case, you can transpose everything and be happier. And then what I want to point out, all right, so F321, 645, how did I get that from 321 and 312? Yeah, I'm sort of concatenating them, and I have to shift the later values. And so if we compute this, you can check via our rule. It should be the sum of these 4 Schur functions, S32, S311, S221, S111, or 2111. And the way that you can I guess one way you can think about it is that these green values are the ones corresponding to the 312, and the purple values are the ones corresponding to the 321. And so the takeaway I want to emphasize, right, 1, this is an example of the Peary rule that we saw earlier this week, but 2, this is the product, and I guess I forgot to write that. So let me write that right now. F321, 645 is equal to S21, i.e. F321, times F312, i.e. S11. And so this expansion of the Stanley symmetric function is a method of computing Littlewood-Richardson coefficients. It's more general than that, but it is a method. And I think I would say that this is pretty different than the method that Anna showed us at the start of last week. OK, so then there's this second approach that I mentioned due essentially to Lascaux and Schutzenberger called transition. I'm not going to go into the details except to say that you're doing this sort of recursive argument where you're writing the f function on this 321, 645 as the sum of the f's of the terms below it, And then as you iterate, eventually your leaves will be single Schur functions. So there's these sort of two methods of computing the same quantity, and both of them are giving us new, to us this past week, proofs of the Littlewood-Richardson rule. And then I think Dave gave us a very nice geometric interpretation, which we'll talk about later on. So this is sort of the setting that I want to start with. And now we're going to move to shifted tableau. And they're coming for us in, well, actually 4 flavors. So we operate with a slightly different alphabet in that we have both barred and unbarred numbers. Their values are interleaved. And they behave slightly differently. So you are row strict in the barred numbers, column strict in the unbarred numbers, and always increasing in each direction. Also, you're shifting, right? We don't start from a left justified shape. We sort of cut out this staircase. So these are new but very closely related types of objects. Is that a question? No. And they come, like I said, in several flavors. So when I put a 1 up here, what I'm saying is that I'm not allowed to have any barred entries on the diagonal. If I do allow bars on the diagonal, then I'll put a 2. And then there's this other completely different flavor. No barred entries, but what's going on here? Well, the rows are unimodal. They first decrease, then increase. And then there's some more technical condition that says that one row is allowed to go on top of another. I won't go into the details of that. And then we assign weights in sort of the way that we're familiar. Barred and unbarred entries have the same weight, right? So if I have a 1 bar, I get an x1. If I have a 1, I get an x1. From this, we can sum over all these weights, and we again get symmetric functions. These are what are called the Schur P and Schur Q functions. So the first type of tableau give us Schur P functions, and then it's kind of surprising that the second and third types of tableau both give us Schur Q functions. They give us the same symmetric function despite this very different combinatorial definition. So I want to point out, I guess, first I maybe want to talk about where shifted shapes come from, and also, as a byproduct, where the barred entries come from. So I'm going to redraw the first example. So, sorry. Maybe I'll do a smaller example. So if I have like 1, 2 prime, 3, 3. Sorry, prime is bar. It's just easier to see bar than prime. So there's sort of 2 ways that I can view this. So one option is I can kind of think of this as secretly being a symmetric ordinary shape in this way. And then I would have like a 2 here and a 3 bar here. Right? And so the bar is giving you a tiebreaker between the symmetric entries. And then if you want to add bars on the diagonal, it becomes a bit more natural to just sort of reflect in a slightly different fashion. Right? And here, the rules sort of break if you try to do the same thing, right? This will not be a semi-standard tableau anymore. but it's close. And I think that this is sort of a good intuition for like why you would maybe want two different ways of talking about shifted tableau. As to some intuition about these third type, which are called decomposition tableau, I don't really have a good answer. I don't know a good intuition for how to think about those. They show up quite organically in certain contexts, but I don't know how to relate it to the shiftedness of it all. Okay, so one important thing to note, so if I take a tableau of the first type and I just bar some of the entries along the diagonal, I'm going to get a tableau of the second type. You're never going to violate the column conditions by changing that. And so that's okay to do. And what that tells us is that the number, sort of the q lambda, is just a power of 2 times the p lambda, 2 to the number of rows. So they're very closely related to each other. They're symmetric functions. They actually form a basis for the subring of symmetric functions generated by the odd power sums. So what that means is that a function is in the span of the q lambdas if and only if f of minus x1, x1, x2, dot, 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 equals f of x2, dot, dot, dot. So you can sort of cancel negative variables against positive ones. And if you think about odd power sums, what are you doing? You're taking a negative number to an odd power, it's still negative. If you tried to do that to something even, they'd be additive. So, these symmetric functions also, they are sort of combinatorially nice, like Schur functions. They're also algebraically nice, like Schur functions. They have Pfaffian formulas. A Pfaffian is sort of like the determinant of a skew-symmetric matrix. And they exhibit a similar sort of duality, except with a modification, right? So what I mean by that, Anna's Littlewood-Richardson rule was really not a product rule, it was a skewing rule, right? You took a shape, you cut out part of it, and then you had some conditions. The rule that I just presented on the previous slide, that's really a true product rule, right? You're taking two symmetric functions, you're sticking them together somehow, and you're multiplying. So the duality is that if you wanted to multiply two p functions, that would be the same as skewing a q function. And likewise, if you wanted to multiply two q's, that would be the same as skewing a p. And this duality is witnessed by several insertion algorithms. So there's a Worley-Sagan insertion, which maps a byword to a pair PQ, where P is of the first type, Q is of the second. There's a Heyman insertion, which maps a pair. I think I wrote the AI upside down on the next two. Oops. Oh, no, I meant that intentionally. If you flip a word upside down, it's sort of a duality, but I won't go into that. So in the Heyman insertion, you get the second type as your insertion object and the first type as your recording object. And then Serrano has an insertion where the first type is a decomposition tableau, this kind of weird unimodal thing, and the recording object is of the first type. So I mentioned, right, clearly there should be some sort of bijection between the second type of shifted tableau and the decomposition tableau. It's not exactly an open problem because you can sort of compose the Heyman and Serrano bijections to produce something, but it's not intrinsic to the objects. You have a whole bunch of intermediate data that's really superfluous in order to produce this bijection. And so I think it would be really interesting for those of you who love Tableau if you thought about trying to construct a direct bijection between shifted semi-standard Tableau of this second type and decomposition Tableau. And I can maybe comment briefly about what's hard about it. what's hard is, so this reading word description of that we used in interpreting Stanley symmetric function coefficients, it's not actually easy to take reading words of these shifted tableaux in the sense that relating the reading word to the insertion is challenging. On the other hand, for decomposition tableau, it's easy. The problem with the decomposition tableau is, what does skewing mean? I don't know. I would consider that an open problem. If someone does know, please let me know. I'm very curious. So these are sort of the flavors of objects that show up. And so far, I guess you could call this combinatorics. So where does the geometry come in? Okay. Nope. Cool. Okay. So there's two geometric contexts where these shifted tableaux occur. And when I say where the, oh, Vasu, yes. Oh, yes. Thank you. Let me write that down. I'll write it over here. Right? So these decomposition tableaux, what does it mean to skew one of them? Okay, so back to the geometric context. So there's two geometric contexts, each that comes in two flavors. So the first one, we're going to talk about the orthogonal and Lagrangian Grassmannians that Frank mentioned. I guess I am omitting that's not true. Okay, cool. So for convenience, I'm going to deal with a vector space which is of dimension 2n, and I'm going to think of the first n coordinates as Cn and the last n coordinates as the dual of Cn. And this is really, it's just a notational convenience, but it makes life a little easier for these definitions. So this vector space comes with two canonical inner products. The first one is to inner product v1 and w1. So remember, v's are vectors, w's are dual, right? They're functionals. And so that means that they're evaluated at vectors. So we can define an inner product where we apply w1 to v2 and w2 to v1. And the plus inner product is where you add those two things. The negative inner product is where you take their difference. And you can actually define the orthogonal group as the matrices that preserve that first inner product, and the symplectic group as the matrices that preserve that second inner product. So you could take this as definitions. Is D 2n or 2? D is even and okay. Thank you, Frank. No, that's fine. Yes, so I was going to say I'm omitting that type D is the same as type B combinatorially. And now I have to say I'm omitting that type B is the same as type D combinatorially. All right. Geometrically as well. Great. And so the Lagrangian Grassmannian is going to be all the vector spaces that are dual to themselves with respect to the minus inner product. And the orthogonal Grassmannian is going to be all of the vector spaces that are dual to themselves with respect to the plus inner product, except there's an issue, which is that there's two connected components in that set, and so you have to pick one of them. So this set in set builder notation is actually not connected, and so you're going to pick the component that contains, say, all Cn plus just 0. So these, right, so since they are preserved by the orthogonal and symplectic groups, you have symplectic and orthogonal actions on them. And so for the Lagrangian Grassmannian, we get a symplectic action. For the orthogonal, we get an orthogonal action. And you get orbit closures, just like we did for the ordinary Grassmannian. You get Schubert cells. The Schubert cells now are indexed by shifted partitions that fit inside of sort of a shifted staircase, right? And the way to think about it is with this sort of intuition, as before. Right? So you're basically dealing with a symmetry in your cells, and that symmetry is reflected inside of this shape. So that's why when we're saying that you live inside of a square, the reason is like in the ordinary Grassmannian, you'd be in a square, so when you do this symmetry imposition, you're in this shifted staircase. And so then it's a theorem, and I'm not sure who to attribute to, and that's my failing. Is it Pragach? Pragach, okay. So Pragach proved that the Lagrangian classes are these sure Qs, perhaps up to some change of variables, and that the orthogonal classes are these sure Ps. So these shifted tableaux have a very fundamental role in understanding Schubert calculus. Right? The Qs for type C, the Ps for types B and D. And then you can extend these to sort of flag-like objects. They're sort of I guess, orthogonal and symplectic flags in the same way that we have the full flag variety. And those orbits are indexed by signed permutations, whose combinatorics I'm not going to get into, except to say that they have Stanley symmetric functions. And those Stanley symmetric functions, again, are sure P and sure Q positive, P for type B/D, Q for type C. And the way that that comes about is this Krushkevich insertion. So Krushkevich introduced this insertion. I'm attributing this result partially also to Tao Kai Lam. He's the one who did the type D case and also worked out the details of the insertion. And so it's the same sort of flavor as our Edelman-Green example for the ordinary Stanley in type A, except the P object is now an increasing decomposition tableau, whatever that means. And the Q object is a semi-standard tableau of type 2. Well, yeah. And I do want to highlight a result by Billy and Lam. And this Lam is not Thomas Lam, but rather Tao Kai Lam, just so you all know, that these actually can't compute products. Nor, I believe, can they compute skewing. Yeah, Alan? That's a good point. So what I mean by that, I think, is that one of these functions will not compute a product. And the way that they can prove that is, well, so what's the fundamental issue? You have to know a little about sign permutation. So a sign permutation is an ordinary permutation, except that every number also has a sign. And so the issue is, let's say I want to stick two sign permutations together in the same way that I did with the Stanley symmetric function for type A. If V has any negative entries, this is not a good map. And so because of that, I can really only use these Stanley symmetric functions to compute this product when V has no negative entries. And you can describe what sort of sure P's and what sort of sure P's or sure Q's can show up for an ordinary permutation when V has no negative entries. So perhaps I'm saying something a little stronger than is true, but at least in a naive fashion, in the same way that we did before with this direct sum construction, you can't compute products. Does that answer your question, Alan? Okay. Actually, maybe, oh, that was a little far. Okay, so before I move on, I guess I do want to pause here for questions. Cool. So the second geometric context I want to introduce is actually closely related to what Anna was talking about earlier today, these k-orbits, or symmetric spaces. So Anna was talking with these clan objects about GLP cross GLQ orbits in the flag variety, right? Type A flag variety. What we're going to do is we're going to act by the orthogonal and symplectic groups on the type A flag variety. It's not obvious that this is a good thing to do, but these are sort of those three examples, these 2 plus GLP cross GLQ, are the 3 types of subgroups of GLN that act on the flag variety with finitely many orbits besides, you know, Borel's. So, and I guess parabolics. Okay, so we have these new actions. They act with finitely many orbits, and it would be interesting to know what those orbits are, and I've written the answer down. So the ON orbits are indexed actually by involutions in the symmetric group. And the SP orbits are indexed by fixed point free involutions in the symmetric group. So I have sort of a construction up here, but it might be a little easier to understand if I write it down again on the board. So what's the idea? So the idea is, right, so I'm taking the flag variety, and I guess I'll do 2n for convenience's sake. Right, what is this? This is GL of our vector space V. And then I'm going to act on, I guess, the left by the Borel. And now what I'm going to do is I'm going to act on the right by the orthogonal group. So I sort of have 2 actions. In principle, there's no reason I can't do that action first and then act on the Borel second, right? And when I do that, if I think about GLV, and I take something in here, I can sort of think of this as like A times O. And then I'm going to construct this map into GLV. And what I'm going to do is I'm going to take this to AO transpose. And what does that look like? That's O transpose A. But what do we know about the orthogonal group? Someone said it. Say it louder. Yeah. O transpose is O inverse. And so now we're looking at AA transpose, i.e. a symmetric matrix. And what is the Borel doing? Well, it's acting on the left by B and on the right by B transpose, i.e. we're doing row operations down and simultaneously column operations to the right, say. And what that means is that you can sort of clear things symmetrically And when you clear symmetrically, you get involutions as your indexing objects in much the same way that you get permutations in type A in the ordinary way. So that's the outline. And I guess it's worth remarking, right? You're not just getting GLV here, but you could replace this with symmetric matrices. So I'm not going to go through the details of the symplectic case, but basically all you have to do with this map is you have to stick your sort of your J matrix in the middle so that you get the same type of cancellation. And so you'll get a skew symmetric matrix as a byproduct. And then if you think about a skew symmetric matrix, that's just like an involution. It's symmetric, but nothing on the diagonal, i.e. no fixed points. So that's how you sort of see this stratification. And then these should have classes in just the ordinary cohomology of the flag variety, type A, right? Our familiar friend. And it's work of Brion and then made a little more explicit by Sean, Joyce, and Weiser, right? These should break down into Schubert classes. And the way that they do is for the ON orbits, it's a sum over permutations 2 to the number of 2 cycles in your permutation. This M2 is the number of 2 cycles times some Schubert class. And then likewise, for the symplectic case, there's no multiplicities. It's just an ordinary sum of Schubert classes, a multiplicity-free sum. And this is the same sort of construction that Anna was using in her talk with clans. So clans represent the GLP cross GLQ orbits, and it's really a general theory that you get this type of decomposition. And she was applying that theory in that case. And so understanding which permutations show up, that's an interesting piece of combinatorics. We're maybe more interested in these polynomial representatives. And so you can just plug in Schubert polynomials. And, sorry, was there a question? Okay. So you can just plug in Schubert polynomials to these sums, and you can define involution and fixed point free involution Schubert polynomials. This is, I guess, I would attribute that to Weiser and Yang. And likewise, you can plug in Stanley's, and you get fixed point free and involution Stanley symmetric functions. And now the final, or the theorem that I'm going to state is where are the shifted tableaux? Well, they come from these Stanley symmetric functions. You actually get Schur Q and Schur P expansions that are non-negative. And what's nice about this is that you can do this sort of direct sum construction for involutions. So you can use these Stanleys to multiply Schur P's and Schur Q's. It's a benefit of this construction that isn't present in types B or in the orthogonal and Lagrangian Grassmannians. All right, so I'm going to sketch 3 proofs. One is via insertion algorithms. So it's very similar to the Stanley construction. You have analogs of reduced words. The same sort of T operators that Anna defined also apply in this case, except there's no minus and pluses to worry about. And so you can define chains via that. Those are your reduced words. You can insert them, and you get this sort of tableau formula in terms of reading words of increasing shifted tableau. So there's an example, F321 in the involution setting. That's Q2. And then if you wanted to do 321,654, that's like F321 squared, or Q2 squared. And then this expands via the insertion into 2 copies of Q31 and 1 copy of Q4, except it comes with a weight of 2. And so it's a little annoying. You have to stick the 2 in. And the reason I'm citing 2 different insertions is that the first insertion, you had to stick the 2 in. The second insertion, you can sort of move the power of 2 into the words that you insert. And it's shocking how much complexity goes into that modification. And then in the SP case, there's also an insertion due to Marburg. So HMP stands for Hamaker, Marburg, Pulowski. And then the other 2 insertions are both due to Marburg. Now there's also transition equations, which we introduced. And so you can do the same sort of tree construction that we did for the ordinary Stanley case in this setting. And as a byproduct, you get Littlewood-Richardson rule for multiplying Qs. It's an open problem to find a geometric interpretation of this transition equation. We came up with it in a purely combinatorial fashion. We don't know what it means geometrically. I think it probably is something that makes sense if you look at the cohomology of G mod K rather than the K orbits, but maybe that's wrong. I'm not sure. So I think this would be an interesting thing to understand for those who are interested in the symmetric spaces, is where does our transition equation come from? There isn't an analogous thing in the clan setting that Anna talked about. All right. Now there's also a geometric context where this appears. And to do that, we're going to introduce something very closely related to what Dave was talking about at the end of his talks, which are graph Schubert varieties. So why do we call it the graph? Well, it's like, you know, when you draw a graph, you're plotting the input and the output. So the graph of a linear transformation is the set of pairs input, output. And if you think about it, graphs, right? So if you do this for all homomorphisms, you get an embedding of G into the Grassmannian of GRn2n. And you're essentially hitting the large dense orbit, right? You're always inserting something that's invertible, right? You're always getting, you can sort of think of it as you have all of Cn and then some other stuff in the dual setting. Okay, and so then you can define. Yes, thank you. Okay, so then you can define a graph Schubert variety via sort of rank conditions. So for your flag, right, you can embed the jth part of your flag into Cn, apply F, restrict to the ith part, and you can ask what is the rank of that map. And that should satisfy the same sort of rank conditions that we've been seeing all week. And it's a theorem of Knudsen, Lamb, and Spire that the class of this is a Stanley symmetric function. So this is a geometric interpretation of the Stanley symmetric function. I guess if you were at Dave's talks, he was doing sort of a similar construction where you had sort of 2 copies of identity and then a whole bunch of stars. And then through that, he was sort of getting the full Schubert polynomial. And you could sort of think of what we're doing as just limiting your focus to this top half. And that's putting you in the Grassmannian, where you get just the Stanley symmetric function. You're sort of losing information. Okay, and then Brendan, a couple years ago, Brendan Pulowski, constructed similar constructions in the Lagrangian and orthogonal Grassmannians just by insisting that our linear transformation either be symmetric or skew symmetric. And so these have classes that are the involution and fixed point free involution Stanley symmetric functions, i.e. they are geometric interpretations of these symmetric functions. Furthermore, this construction can sort of be back stabilized and you can get backstable polynomials as well. So I have, what, about 5 minutes? Is that right? All right, so you can also think of these in sort of the matrix setting, i.e. affine space. And here you have symmetric matrices and skew-symmetric matrices. So in the symmetric matrices, you can sort of think of it as you have rank conditions in two directions, right? Either you can read from the upper left or you can read from the bottom right. For all matrices, that's roughly equivalent, right? Like Laura's row indexing being different than what we had been doing, that doesn't really change anything for the algebra, the combinatorics, et cetera. Here, it matters a great deal whether you're reading from the axis of symmetry or away from it. And so if you read towards the axis of symmetry, then you're getting these O orbits. If you read away from it, you're getting type B flag objects. And likewise, for the skew-symmetric setting, you're getting, if you read towards the axis of symmetry, fixed point free involutions as your indexing objects. Away, you're getting sign permutations, again, type C flags. And you have the same sort of correspondence of representatives that you might expect, right? The equivariant cohomology of a matrix Schubert variety, that's the same thing as the double Schubert polynomial. And so you get the same sort of equivariant representatives translating. You can ask whether the Grobner degeneration that Patricia was talking about this week, whether you can sort of get pipe dream-like formulas from the commutative algebra of the defining ideals for these matrices. And the answer is, in the skew-symmetric case, yes. So Marburg and Pawlowski did that. And then the type C flags paper that I'm referencing also does that for the other reading away from the axis of symmetry. For the symmetric case, it's open. It's really hard. I don't really, okay, so the original ideals themselves, I think, are not reduced, which makes life pretty terrible. Yeah, so if you polarize and take the limit, there's some hope. Sorry, what? Limit, then polarize. So that gives you some hope for treating the commutative algebra. I can say with some confidence that the combinatorics that has been worked out is not adequate to treat that case, right? In the diagonal degeneration case where multiplicities occurred, we still have combinatorics that governs the whole story. We don't quite know how to piece it all together, but the combinatorics is there. In the symmetric story here, we've developed an equal amount of combinatorics as in the skew-symmetric case, but it's just not adequate. It doesn't tell you everything that you would hope for. And so someone has to be really clever to work this out. And maybe Alex has done that, I don't know. Okay, so I should wrap up quickly. I guess maybe the one thing I want to conclude with, the details on this slide are not so important, except to say you can do all of this in K-theory. When you do that, there are rules for multiplying G's. There are rules for multiplying GPs. There is no rule for multiplying GQs. So G's are coming from the K-theory of the Grassmannian, GPs from the orthogonal, GQs from the Lagrangian. There is no way to multiply GQs that we know of. In fact, I don't know that there is, I guess, I mean, they have, I don't even know of an easy way to compute them, and I'm sure other people in this room do. But combinatorially, they are not well understood. There is a Pieri rule, so I guess that would be a way to compute them. But that's, I think, the state of the art. So you can do G lambda times G single row. I don't think anything more is known. GQ lambda times GQ single row, sorry. And so why is this hard? Essentially what it boils down to is that all of the Q rules that we know for not GQ but just Q are really just P rules, and then we add the powers of 2. And the Marburg thing that I mentioned is really the first Q rule that I'm aware of that is truly a rule for multiplying Qs. It doesn't just do the P's and add the power of 2. And so since GQs are not just a power of 2 away from GPs, that trick doesn't work anymore. Life gets worse. And like we discussed, you either don't know how to skew or you don't know how to read. You don't have a reading word or you don't know how to skew, and those are sort of the 2 tools that we generally have. So I have some work in progress where we're sort of, if I go back a few slides to the first geometric context, I mentioned this Krushkevich insertion. We're doing, so I have some joint work in progress with Josh Arroyo, Jianping Pan, and Graham Hawkes, who isn't here, where we at least have defined a K-theoretic version of Krushkevich insertion. We're still working out the details, but the payoff would be, at minimum, that you should be able to prove the Buch-Ravi-Kumar-Pieri rule combinatorially, and a bit more. But like we mentioned earlier, it's not easy to multiply Qs via a Stanley symmetric function, and this would only let you compute sort of K-theoretic Stanley symmetric functions, i.e. it shouldn't be able to do all the products in GQ land. Okay, so I think that's where I'm going to end. Thank you so much.